Okay, Fulvio, should we start?
Yes.
Okay, I'll announce you. Just a second. Right, hi, everyone. Welcome to the second talk in this morning session on the fourth day of the optimization, symmetry and optimization under symmetry workshop. So it's great to have Fulvio Gesmundo joining us from MPI Leipzig from Germany right now. And he's going to tell us about optimizing on network tensor network varieties.
Thank you. And thank you for the introduction. And thank you for inviting me to speak. And I'm very happy to be back at the Simons Institute, even though virtually. And yes, I would have enjoyed to be there in person, but I couldn't join. And today I want to tell you something about a work that we did like last year together with Matthias Christandl, Daniel Stilfranza, and Albert Werner, where we studied ways to run optimization methods on tensor network varieties. And so I will start telling you what a tensor network is. And so tensor network states are tensors in tensor product of complex vector spaces. And in this talk, L, big L, will always be the order of the tensor, the number of the tensor factors. And tensor network states are tensors that arise via some particular tensor contractions, which are encoded in the combinatorics of a graph. So if you were in Matthias's talk yesterday, Matthias sort of introduced these and kind of gave a preview to my talk, and in the last part of his talk. And in his setting, the setting he described, the setting was a little more general, like he considered hypergraphs, not just graphs. And in principle, everything that I say applies to the hypergraph setting that Matthias described, but it's like there are a lot of technicalities that one has to be careful of that. So I just want to present it in the case of simple graphs. And so let me tell you that tensor networks like appear in quantum many-body systems, in quantum physics, where they were studied in the context of quantum physics under this name, but they appear in a number of different fields. So yesterday in Peter Burkisser's talk, algebraic branching programs were mentioned, and algebraic branching programs are a polynomial version of tensor networks. And in machine learning, there are linear networks, deep linear networks in particular, that are nothing else than a particular case of tensor networks, where in machine learning one wants to introduce some non-linear factor with some, there is like some non-linearities introduced, but they're essentially tensor networks. In algebraic statistics, there is a probability model. There is a generalization of Markov models that are called graphical models, and under some identification and under some duality, these are essentially tensor networks. And a particular case of a graphical model in mathematical biology is what is a phylogenetic tree, which describes evolution of species. And this again is a tensor network on a tree in particular. And from a geometric point of view, these tensor networks form algebraic varieties. These tensor network states form algebraic varieties, which have a rich representation theoretic structure. And I like geometry, I like representation theory, so I like to work with these things. And algebraic geometry can say a lot of things about this set of tensors. So if there is any question, like please interrupt me at any time. So to tell you precisely what these tensor networks are, I want to introduce the definition of a graph tensor. And a graph tensor is a tensor that is associated to a weighted graph. So like the elements are a graph, like a graph where a set of vertices v of gamma and a set of edges e of gamma, and a set of integer weights on the edges. In this case, I have a picture of a triangle with weights m1, m2, and m3. And these weights are called bond dimensions, usually. and L, the number, I will cook up a tensor on L factors, and L will be the number of vertices. And so to construct this tensor, I first attach an identity matrix on each edge, on each edge of my graph, on identity matrix of the size equal to the bond dimension. And so here I'm sort of cheating a little bit. I'm identifying a primal and dual, but I want to think of this identity matrix as an identity that maps a vector space on one end of my edge to the other end of my edge. And so I have these identity matrices, one on every edge. And now I tensor them all together. And when I tensor them all together, I get this big tensor with as many factors as twice the number of edges. So I have the first identity matrix that is in CM1 tensor CM1, and then the second in CM2 tensor CM2, and the third one in CM3 tensor CM3. I tensor all of them together, and I get this tensor on 6 factors. And now what I do, I want to group together the factors that correspond to the same vertex, that are at the same vertex. And I regard this big product, this big identity, as a tensor on L factors, on as many factors as the number of vertices, where my factors have some inner tensor structure, so which in some way I want to forget. I want to forget that these inner factors have this tensor structure. I just want to view it from outside as a tensor on L factors. And I will call WV, like V is a vertex, small v is a vertex, and I will call W's these big factors. And so I get my graph tensor is this tensor on L factors, which is constructed in this way. And the notation will be T gamma for the graph and M for the bond dimensions. And from this tensor, I want to construct a variety. And I want to construct a variety inside some other tensor product, some tensor product V1, tantata, VL, where the dimension of the DJs are NJs. And to do that, I look at this map. I look at all possible L tuples of linear map, mapping the WV, the W space corresponding to vertex V, to the V space corresponding to vertex small v. And I just hit my graph tensor with this L tuple of linear maps. And in this way, I let these linear maps vary, and I get a set. I get a set that is the image of this evaluation map. And I call these, I use this notation TNS for tensor network states, and with a little circle up here. This is not yet a variety. And when I take the closure, and this closure is equivalent if you take in the Zariski topology or in the Euclidean topology of the complex vector spaces, I get an algebraic variety. And this algebraic variety is the tensor network variety that I'm interested in. So it is defined as the image of a polynomial map, phi, which is just evaluation of a bunch of linear functions, of the tensor product of a bunch of linear functions on the graph tensor. Okay? And okay, let's look at an example, a very simple example. So we consider the graph with just two vertices and two vertices and one edge, and M will be the bond dimension of my edge. And in this case, the graph tensor is just an identity. There is only one edge, so it's just there. And it's an identity from W1 to that is a CM on this side, to W2, which is a CM on this other side, on the two side. And now I pick two vector spaces, V1 and V2, of dimension N1 and N2, and my evaluation map just maps two linear maps, which are a matrix of size N1 times m, and a matrix of size n2 times m. And with this pair of matrices hits this identity matrix. And if you write everything in coordinates, you see that this is really picking, multiplying on one side is the identity by x1, and on the other side by x2, but to make dimensions work, I have to take a transpose. And so this is like this x1, x2 transpose is the image of my phi as these linear maps vary. And in this case, the tensor network, this open part of the tensor network variety are just matrices in V1 tensor V2 of rank at most m, because they factor as an n1 by m matrix times an m by n2 matrix. And in this case, it turns out that in fact this is already closed. I don't need to take a closure. Okay. Is there any question? Okay.
Good.
Yeah. Okay. And let's say some easy property of these graph tensors and of these tensor network varieties. So if I have an edge of weight 1, is the same as not having an edge in the graph. Because if I have weight 1, really in my graph tensor, I just have a 1 by 1 identity matrix that then when I hit with the linear maps, I just have a scalar floating around. But the scalars will be there anyway, because I have them from the other linear maps. So in the rest of the talk, I will always assume that my weights are at least 2. And there is a multiplicativity property where if I take two graph tensors on the same graph and I take their Kronecker product, this is the tensor Kronecker product, which is like the tensor version of the matrix Kronecker product, where I multiply my tensor by taking their tensor product and then grouping together factors that are in the same position. This is the same as taking the graph tensor of weight where I take the entry-wise product of the weights. And this is because I'm Kroneckering together these identities on each edge, but the identity of size m times the identity, Kronecker the identity of size m prime is just the identity of size m times m prime. There is a monotonicity that, if you want, comes from this property, but it's a little more general, that if m prime, if m is larger than m prime entry-wise, then the tensor network varieties are one inside the other. And there is a universality property where it says if gamma is connected in the sense that I mentioned at the first point, where all the weights are at least 2 and the graph is connected, then if the bond dimensions are large enough, the tensor network variety fills the space at some point. And in fact, also, if m is large enough, also the open part, like maybe for larger bond dimensions, but also the tensor network variety with a little circle, with the open part is fills the space eventually. And then there is like some geometric property, reducibility and invariance under rescaling, that I have my variety is defined as the closure of the image of a polynomial map with an irreducible domain, which is just a product of Hom spaces. So in particular, it will be irreducible. It is a irreducible variety, and it's invariant under rescaling. If there is a tensor, there is also every scalar multiple of that tensor. And so it honestly defines a variety in projective space. I can identify it with its projectivization. Okay, this is some easy property that will be useful later. And let's see why we care about these varieties. And here I will be a little sort of like a little vague, but the idea is that it is easy to evaluate graph tensor if you compare with the evaluation of other tensors in the same space. So graph tensors are so structured that it's easy to evaluate. And you can think of this evaluation in more or less the way that you want, like tensors correspond to multilinear maps, and you can think of this as evaluating the multilinear map. Or you can, if you are from the quantum information community, your evaluation is to consider some, for example, evaluating some observable on your tensor. And this is some sort of tensor contraction with a big matrix. And if you do it for graph tensors, this is easy. This is easier than other tensors in the same space. And so what's the strategy? Say that I care about a tensor T in Cn, tensor Cn, and I want to find a tensor network representation from my T. So maybe I choose a graph, gamma, and with small bond dimensions, so that I know that evaluating the graph tensor is easy. And then I hope to find these linear maps. Maybe I know my tensor and I run, again, some numeric, some optimization process to find this tensor. To find this an L tuple of linear maps that they give a tensor network representation for my tensor T. So that realize my tensor T as image of the graph tensor. And then I use the fact that I know how to evaluate the graph tensor to evaluate T. And here I'm swapping a lot of stuff under the rug, but this is more or less the idea. And the strategy uses the open part. I want to find this axis, the open part of the tensor network variety as an ansatz class for a good tensor network representation of my tensor T. And it's known that there is a class of tensor of physical interest, which is what also Matthias mentioned last morning, which are these ground states of local gapped Hamiltonians, which are known to have good tensor network representation. So if I know that my tensor is a quantum state that describes the ground state of a local gapped Hamiltonian, then I know that there will be a graph which sort of depends on the geometry of the system and small bond dimensions which for which this representation exists. And so I want to find it. And there is a natural question, which is what happens at the boundary? So what if my tensor that I care about lives in this difference? So when I try to run some optimization method, when I try to run some numerics, this will not work because maybe these x1 tata xl don't exist. I mean, if it lives in the boundary, they don't exist, but I can approach my tensor arbitrarily close. And usually what happens is that the problem becomes ill-conditioned. When you run these the numerics, the entries of these matrices explode and things like that. And so there is another question of what can I do in those cases? And of course, I have a
question. Just a second.
Yes.
I have a question about this statement that ground states of local gapped Hamiltonians have good TNS representations. Is this a heuristic statement or this is a theorem? And also, what is the underlying network if you really assume that the system is living anyway on a graph like
right. So if you it depends on the system, it depends on the graph. So for what are called matrix product states, which are tensor network where your graph is a path or a ring, then they're known to have, I don't remember off the top of my head the parameters, but then given the local dimension of your tensor, and then it is known that there is a matrix product, and you know that it is the ground state of a local gapped Hamiltonian on a path or on a ring, then they're known to have good tensor network representation. And for other things like PEPs, MERA, other type of graphs, I think it's not very well understood what if it is precisely. Like yesterday, Matthias mentioned this area law, which plays a role in this construction, but I don't know the details.
I think that the area law will just tell you that there is an approximation which doesn't, that looks like
Yes, where
But the approximation is not in your formulation of the variety. You also want, I mean, you want to find the point in the variety.
Yes, yes.
You would need a point that's close to the variety.
Yes, I agree that the for the area law only gives you. Well, I think it depends a little bit on the settings, but in principle, yes, the area law only tells you that you can approximate it well with respect to the parameters of the system. Right.
Thanks, Fulvio.
Yeah. Okay, so let's. Is it okay? Can something happened? No. Okay.
No, go ahead.
So let's see what can we say about the boundary. So there is a theorem which I state again like in sort of an imprecise way, but this is sort of the idea of the theorem, and there are like there is some range in the precise statement, which is in some range was proved by Landsberg, Bianchi and Caillet in 2012, and this year, like Vattel when Frieseke refined this statement, where like if gamma doesn't have cycles, then the tensor network, the open part of the tensor network variety is already closed. You don't need to take closure. And if gamma has cycles, then the boundary is non-empty, unless it is empty for trivial reasons. Like for instance, maybe the bond dimension is so large that this already fills the space, and then of course the boundary is empty. And other things like that can happen, but I don't want to get into technicalities. And further, in a work of 2020, Christandel, Lucia, Vrana, and Werner proved that sometimes in some setting, these tensor networks that are ground states of locally gapped Hamiltonians lie on the boundary, in the sense that, yes, you can find a good tensor network representation, but even if with even smaller bond dimensions, you can prove that they are in the boundary. Also for some smaller bond dimension. And so what we try to do is that we determine the nuances class with two properties. So these evaluation properties that are easy for the tensor network nuances class are still easy in the nuances class. And this class includes states at the boundary. So we can reach a little bit of the boundary. And to do this, we use the geometry of the osculating spaces of this variety. And in the rest of the talk, I will try to tell you a little bit more about this.
There's another question for you.
Yes?
Hold on.
Hi. All this stuff, does it like this ansatz, is it like related to beta ansatz? Because in beta is also you start with like a system without like on trees, no cycles, and you approximate the general. So again, so there is this in statistical physics phenomena that if you have if it's no cycles, you can compute partition function efficiently. And in general, you need to do this beta ansatz, which is good. So anyway, did somebody study, is it like some kind of a quantum generalization of beta ansatz?
I don't know.
Thanks.
I know for like, if you consider like, for instance, I don't know if this is related, but for tensor network representation, for instance, on binary trees, are related with this hierarchical Tucker decomposition of your tensor. I don't know if this is related in any way, but I don't know.
Can I make a comment and also ask you a question for you?
Yes.
So I think people, I mean, I don't know the full answer, but I think people have studied, they've used the beta ansatz to construct, for example, matrix product state, so these one-dimensional tensor network descriptions in some special cases, but I don't know if there's a general correspondence or inclusion or something like this. The question I want to ask is, maybe you mentioned this, but if you make the bond dimension larger, do then things that previously were in the boundary somehow become now part of the interior or something like that? So
yes, and I will say something about that in a second.
Okay.
Yeah, I will say something more precise about that in a second. Yes, of course, you can always make the bond dimension larger, but that's kind of an expensive way to get stuff at the boundary. But I will say more.
Because you're okay. And can I ask about the evaluation being easy? I mean, in general, if I have like a general graph, it's not easy to compute with tensor networks.
Well, yes, that's true. It's not easy, but it's yeah. Again, it was sort of vague, but it's still easier than a tensor in the same space. Than if you take a general tensor in the same
to
space.
Represent, I guess.
If I have even if I have a PEPS representation, it's better than having no representation at all. And of course, like if you have a matrix positive state representation, it's particularly easy. If you have like 3 representations, it's easier.
And easy then for you kind of means sort of as easy as sort of an ordinary tensor network on the same graph, or kind of the same order of magnitude.
Yes.
Oh, okay. Thank you.
Okay. Let me introduce this definition of restriction and degeneration, which is also what Matthias mentioned yesterday. And we say that a tensor S in a product of W vector spaces and restricts to a tensor T in a product of V vector spaces, where if there are linear maps such that I can realize T as the image of S, and I say that it is a degeneration if I can do this after possibly passing to a limit. So if my tensor, I say that S degenerates to T if T is a limit of restrictions of S in this sense. And with this terminology, this open part of the tensor network variety is the set of all restrictions of my grasped tensor, and the actual tensor network variety is the set of all degenerations. And so as Michel was mentioning, like there is an easy way to pick up tensors at the boundary, which is just let's make the bond dimension bigger, and eventually we will fill the space. So in particular, at some point we will get tensors at the boundary. And let's see how we can do this. Well, there is an easy way, which I mean we didn't find it in the literature, but it's sort of so easy that had been known for sure. And if say that T lives in the tensor network variety with bond dimension M, and now, but for simplicity, I'm always taking like local dimensions to be all the same equals to small n, and the bond dimensions to be all the same equals to small m. And say that my T, I can express it as a degeneration of the graph tensor of bond dimension M, then it is a restriction of the graph tensor with bond dimension big M for some m which is bounded above by a power of the small m, where this power only depends on the combinatorics of gamma. In particular, it does not depend on the bond dimensions, and it does not depend on the local dimensions. And I give you a very fast idea of the proof. So there is a path. If I have a path, like the tensor network on a path, then the graph tensor on the path restricts to the edge joining the extremes of the path. And this in quantum information is called quantum teleportation. Or in geometry, it is like usually called just a flattening argument. And this means that the tensor network on the path restricts to the tensor network which only has one edge on joining the two extremes of the path with the same bond dimension. But then I can use my multiplicativity property. I can pick 2 copies of these and tensor them together. I restrict one to the opposite edge, and I realize the graph tensor on the triangle as a restriction of the graph tensor on the path with squared bond dimension. And but this tells me that every degeneration of the graph tensor on the triangle with bond dimension m is a degeneration of the graph tensor on the path with squared the bond dimension. But the path doesn't have cycles, and so its degenerations are restrictions. And since all its degenerations are restrictions, I realize my all the degenerations of the triangle as restrictions of this path. And in general, the argument is a little more complicated when where you have to replace the path with spanning trees, with a spanning tree of your graph. And if you are a little, then you can use this argument to sort of like cover the missing edges from the spanning tree. And that's why you, in principle, you need more than more than the square here. And
sorry, can I just ask for like a square grid of say n by n square grid, like a k by k square grid, like
yes, then this is very
k?
Yes, this is very big. This becomes very big.
Okay, okay, so it's horrible.
We have the number in the thing, but it's some yes, it's something like I think at least quadratic in the size of the grid.
Okay.
Well, no, okay, maybe quadratic is too much.
But it's just like not constant, basically, like it really grows.
No. If you enlarge a graph, it gets bigger. Yeah. And so this argument is completely topological. It doesn't tell you anything. Doesn't tell you how to do it at all. So let's try to do a little better. And to do a little better, I want to tell you something about how degenerations look like. Well, if S degenerates to T, then I can find these linear maps that give me a path to, well, give me like a curve on of restrictions of S that converges to T. And I can do this with choosing linear maps which depend polynomially in epsilon, polynomially in a parameter on the curve, and I can express this in this way, so that my restrictions look like epsilon to the a for some constant a times t0 plus higher order terms which depend polynomially in epsilon, and when I pass to the limit, I divide by a power of a power of epsilon in this way, and I get t in the limit. So this t0, this leading term of my curve, is the tensor t that I care about. And we call this a, the thing that I divide by, the approximation degree, and e, the error degree. E is the number of terms that I end up with up here. And these numbers tell us how far the degeneration is from being a restriction, how much is really a limit rather than a restriction. And from a geometric point of view, E is the degree of the approximating curve in projective space, because like if you, in projective space, you divide by epsilon, this epsilon to the A washes out, and you are left with a curve of degree E. And A is a little bit more complicated, and we'll tell you toward the end what is its role. And now we can use this E to get a better bound than the one before, or at least like a more explicit bound. So let's say that T is, and this was like first idea on tensors of order 3 is due to Bini and Strassen from the 60s and the 70s. And then in this work by Matthias, Angelo, and Peter and Albert, they proved that they wrote it down explicitly for graph tensors and for tensor networks. So let's say that T is a degeneration with bond dimension M. So it lives in the tensor network variety with bond dimension M, possibly at the boundary. But I know that my degeneration has error degree E. Then I can show that T is a restriction of the graph tensor with one dimension big M, where this M is bounded above by E plus 1 times small m. And well, I give you an idea of the proof. As we said before, E is the degree of the approximating curve, and the points on the curve, at least generic points on the curve, are restrictions, are honest restrictions. And there is a classical fact in geometry that E plus 1 generic points on a curve of degree E have the same span as the whole curve. So in particular, E plus 1 points on the approximating curve span the limit point. And what I can do, I can pick E plus 1 points, and if I can simultaneously do these E plus 1 restrictions, then I can interpolate to the restrictions and get my point in the limit. And this is how the argument works. And so there is a problem, of course, here, that this E is something that is very hard to control. It's not, nobody knows how big it can be, or like also it most certainly depends, like as the number of vertices grows, this E, like the possible E's will grow, like the highest possible E will grow. And so again, this is it, but we get about. And now we would like to do something which doesn't just increase the bond dimension, but does something slightly different now. And to do that, we want to use this approximation degree. And I recall from before that my degeneration, my approximating curve, looks like epsilon to the a times t plus higher order terms, higher order in epsilon. And these axes, these linear maps, depend polynomially in epsilon, so I can write them in this way. Xj of epsilon will be a sum of some curve of in the space of linear maps, which depends polynomially in epsilon. And well, what is this tensor product? Here I'm just expanding this tensor product of all these summations, and I expanded in powers of epsilon. And this is how this sort of like multinomial formula for tensors. So I don't know how to call it, but this is what you get when you expand everything. And you get this sum over, like, to get the term of degree p in epsilon, you get the sum over all the possible pieces that add up to p. And well, if this in the end is epsilon to the a times t, what should happen is that if p is less than a, then when I hit my tensor S with this big linear map, then I have to get 0, because that doesn't appear in my curve. And when I hit it with the piece of degree a, I will get t. So the point is that, what if I was able to just hit S with this piece? This is the problem is that this is not a product, a tensor product of linear maps. So I'm not allowed in principle to just hit it with this. And in fact, my t will not be a restriction. But what if I can design a way to just hit my S with this tensor, with this big linear map? And that's what we did. We defined this state that we call the weight state, and this is a tensor in the product of spaces of dimension a plus 1, which is sort of a monomial version of a tensorial version of a monomial. And it's just like if I say that V0 has weight 0, V1 has weight 1, and so on. This is like the sum of all the basis tensor, of all the tensor products of weight A. And I just pick this big sum. And if you want, this is a generalization of tangent vectors to the variety of rank 1 tensors, and are related with higher fundamental forms of the varieties of rank 1 tensors. When A is equal to 1, these are really tangent vectors. And there is an easy observation that I just mentioned very fast, is that if S degenerates to T with approximation degree A, then T is a restriction of S, and here I should have written a Kronecker product with this weight state. And this weight state is symmetric, so it doesn't really matter what factors I give to what factors of S. And using this, we define our nuances class, and which are all the restrictions of the graph tensored with this weight state. And this answers class contains all the degeneration of the graph tensor with approximation degree at most A. And yes, this was like our idea to do this. And so the new class is this. It contains tensor at the boundary, and we prove good evaluation properties in the sense that I roughly mentioned before, in the sense that we can control the overhead like how much more expensive it is to evaluate this canonical product compared to evaluating the original graph tensor. And to do this one, we use two properties that I just mentioned of these weight states. They have minimal border rank, if you know what border rank is, and they have a small tensor network representation. So in particular for these, we can write down a small tensor network representation. So if you want, using the tensor network representation, you can go back to one of the previous statements where you just enlarge the bond dimension. You enlarge the bond dimension so that your auxiliary piece of the tensor network produces this weight state, and you get this method kind of fits in the ones that were there before. So just to recap, so there are these tensor network representations that are useful to do evaluation of tensors, and sometimes it's useful to have a good way to evaluate tensors at the boundary, and there are several ways to do that. To find good tensor network representations for the boundary tensors, we can enlarge the bond dimension, or we try to define a nuances class. And I want to say we kind of run, like none of us is like a numerical analyst, so we sort of picked the existing code and existing methods for tensor networks, and we modified in a way to include these weight states, and we try to run it, and they run better. I mean, it's better than just enlarging the bond dimension. And but we didn't do any kind of precise analysis in that direction. But we can control the overhead in the complexity of doing these calculations. And of course, there is like next. What can we do next? Well, this new class doesn't just contain the original class or tensors at the boundary. It's honestly bigger. It contains more stuff. So there is another question of how much bigger it is. And what are the new tensors good for? Can we use them to describe to give representations of some other tensors that is useful? And with this, I think is what I wanted to say. Okay.
Thank you, Fulvio. So we have plenty of time for questions, if there are any. From the chat.
So does it help you in any way get any better algorithms for matrix multiplication, this new answers class?
Not really, no. We had an example. No, I mean, the simple question is no, because they kind of go in the other direction also. Like the matrix multiplication tensor is the graph tensor associated to the triangle, the one that I showed at the beginning. And what we're doing here, we're doing degenerations of that matrix multiplication tensor. So it's sort of in the other direction. We don't find a good representation. The matrix multiplication tensor is a graph tensor itself.
Yeah, of course, but you can have direct sum of some rectangular matrix multiplication tensors. There are also tensor networks, reduce them, degenerate them to other sums, and maybe
so yeah, we can think. Yeah, okay, we didn't think too much about that. But it might be something interesting to look at. No, I don't know.
Okay,
right now.
Thanks.
There's another one. Second.
So in quantum mechanics, I think one important operation you can do on these tensors is to contract them. Take two tensors and partially contract. Is that an operation which can be represented in terms of the underlying graph? Is that something which means doing something to the underlying graph?
Yes. So of course it depends which spaces you want to contract with which spaces. But in principle, what you do is that you get like two graphs, and then you sort of glue together some of the vertices, and the contraction will be the contraction of the two graph tensors in some particular way that you want to do. And yes, and this is like, you can do it with tensor networks sorry, let me say, in some cases, like, of course, there is like, it depends on the graph, but if your graph, for some particular graph, this can be done very efficiently with graph tensors. For instance, for matrix product states, this is very easy. And for trees, this also is easy. And it's sort of, like, as I mentioned earlier, there is this, when your tensor network is a tree, then this is really with this hierarchical tuckle decomposition. And when you have a tuckle representation of your tensor, doing contraction is easier. And you can do it more efficiently.
Thanks. Questions? Fulvio, I had one question, sort of a basic one. For these tensor network varieties, you know, it'd be interesting to know their equations, right?
Yes, it would be very interesting to know their equations.
And I'm sure it's complicated, of course.
Yes.
But how about, you know, sort of easy cases? Like, what I'm thinking is, if you have a graphical model on discrete random variables, you know exactly when the model is defined by quadratic polynomials.
Yes. So,
is there anything like that for this?
So let me, I'm not sure if there are good settings where you can say that the equations are quadratic. I would be surprised if there are. Unless of course, like, dimensions are very small, or like if the bond dimension is very small. For instance, if the bond dimensions are 1, then you get rank 1 tensors, and they are defined by quadratic.
Right. Right.
But already, if they get a little bigger, I would expect that the quadratic kind of disappear.
I guess, but no, what I'm thinking is like a graphs, like in the, again, graphical models case, if the graph happens to be decomposable, right? If it's a triangle free, no, not triangle free, but chordal graphs, then that's saying that the equations have to be quadratic.
Yes, that's true.
Is anything like that?
I'm not sure, but let me say, like, if you don't have cycles, then you can write everything in terms of rank conditions.
Okay. Okay.
Because you have this flattening. So when you separate, you split your graph, like whenever you touch an edge, you make a cut of the graph. That cut defines a linear map, and the linear map has bounded rank, bounded by the size of the cut.
Yeah. Yeah.
And this gives some equations, and this can you do it in general. Like, we have a work with Michel and J.M. Landsberg where we study these cuts for matrix product states.
So my last question is sorry. Go ahead.
Let me add something, that we have cases where we have all the equations. Well, for some very small case, there is another work with Alessandra Bernardi and Claudia De Lazzari where we look at 2 very small cases, among other things. One is the graph tensor on the triangle with bond dimension 2 and size and local dimensions 3. And in this case, if I'm not wrong, you get equations of degree 8, all equations of degree 8. And then there is another case which is like on the square with bond dimension 2 and local dimensions 2. Your tensor network variety is a hypersurface of degree 6. Okay. Okay. And this degree 6 is, of course, everything is invariant under the action of the general linear group acting on the vertices. And so it is an invariant for this equation, is an invariant for this action, and it has very nice expression. It's easy to check if something is 0 or non-zero.
Okay.
Like, so my last giant polynomial of degree 6. Yeah.
My last question is, so at the very early stage of your talk, you mentioned these properties, and there was this multiplicative property there. So you had the same graph, I think. Yeah, exactly. Same graph, but the m's changed, you know, and then you took the Kronecker product. So when I saw that, I thought about sort of the multiplicative property of the maximum likelihood degree. Yeah. So, you know, if so I mean, I can read this equation from right to left. So you have a tensor network and you're decomposing it, it's kind of into 2 tensor networks. If that happens again, for instance, for graphical models in a nice way, then you can look at the maximum likelihood degree of the bigger model, and that's equal to the product of the maximum likelihood degrees of the smaller model. Is there anything like that here?
And I think that the reason is pretty much the same. If I am not
okay.
Yeah, I think the reason is more or less the same.
Okay.
It's the same multiplicativity. Like if one writes down everything, I think that you get multiplicativity in the graphical model setting because of this multiplicativity, or the other way around.
Okay, good. All right. Thank you. Anything else? Any other questions? Okay. Thanks, Fulvio.
Thank you very much.
Nice talk. And so yeah, again, one more time. Thank you. And yeah, so we're finishing off here, and then there is another talk at 2 o'clock this afternoon. Yeah.
Okay. Thank you again.